Hello everyone, we are still doing our chapter kinetics homework, and I will go ahead and explain you how to do the homework starting from question 17. Dinitrogen tetroxide decompose to nitrogen dioxide in a first order process. We are given K values, rate constants. If K is 2.5 into 10 to the negative 10 to the positive 3 per second and 3.5 into 10 to the power 4, what is the activation energy for the decomposition? And we are also given two temperatures. Okay, so K1, if this is K1, this is T1, and if this is K2, and this is going to be T2. So we're going to use the equation. Okay, I will show you which equation we're going to be using. We will use this equation right here. Okay, activation energy can be calculated using the Arrhenius equation. And also, if you have two different temperatures and data available for two rate constants, so we can use this equation. So this is what you are going to use. We have two rate constants, we have two temperatures. R is the gas constant, so we can use this equation to find out the activation energy. Okay, so let's go ahead and do that. So our equation going to be ln K2 over K1 equals negative activation energy over R 1 over T2 minus 1 over T1. So when you are plugging the information for the temperature, you want to make sure that the information is given in Celsius. You have to convert it to Kelvin. How do you convert Celsius to Kelvin? You add 273 to the negative 5 and also to positive 25. So that's what you're going to be using. So ln K2. So our K2 is 3.5. K2 going to be ln 3.5 into 10 to the power 4. And ln K1 going to be 2.5 into 10 to the power 3. So the units will cancel per second. And activation energy is what we don't know. And R going to be 8.314. And units for R, joules per moles per Kelvin. Okay. So the units for gas constant going to be joules per moles per Kelvin. Okay, and 1 over T2. So our T2 is 25 degrees Celsius. When you are 273, that is 298. Okay, 298. 298. Minus 1 over negative 5 plus 273, that is 268. So it is going to be 268 here. Okay, yeah, and then you do the calculation. So when you do the calculation, ln, so first what you can do is, when you are performing the calculation, first get this part before you get the ln. 3.5 into 10 to the power 4 over 2.5 into 10 to the power 3. Do that in your calculation. That will give you 14. Okay, and then it would be then ln 14 equals negative activation energy over 8.314, and then do the calculation in parenthesis. 1 over 298 minus 1 over 268 in your calculator. That would give you a numbers like this. Negative 3.75 into 10 to the negative 4. Now do not go by my word for these calculations. You also check to see if you are getting the same numbers. If not, maybe I have done something wrong, right? Or if there is anything that my calculations are not correct with what you are doing, please let me know. Okay, so make sure you also perform the calculations yourself, because I want you to learn. So negative will get cancelled. Okay, so 3.75 into 10 to the negative 4, you divide it by 8.314. So you will get a number. So ln 14 would be 2.64, and from the other side it would be activation energy times, when you divide this number, 4.52 into 10 to the negative 5, and then you can find out the activation energy. Okay, and we are doing question number 17, and looks like it is given in kilojoules. So you guys know how to convert joules to kilojoules. You divide it by 1000, because our units over here is joules per moles per Kelvin, and this is going to be Kelvin over here, so that get cancelled. So joules per moles, so the answer would be in joules, and then you can, this answer would be in joules, so you 1000 joules equals 1 kilojoule. So final answer, you can convert it to kilojoules. Okay, that's how you would do number 17. And number 18, ammonia will react with oxygen in the presence of a copper catalyst to form nitrogen and water. From 164.5 to 179, the rate constant increased by a factor of 4.27. What is the activation energy of this oxidation reaction? Again, we are given two different temperatures, and also it tells us that the rate constant increased by a factor of 4.27. Meaning we can still use the same equation that we used for question number 17, because we have two different temperatures, we have two different rate constants, and we can find out the activation energy. Okay, so that's what we're going to be doing. Okay, number 18. So we will be using the same equation like this. Okay, I'm going to leave it like that. First you have to convert these to Kelvin by adding 273 activation energy. So we can consider 164.5 as your temperature 1, temperature 2, and then make sure to convert them to Kelvin by adding 273. Rate constant increased by a factor of 4.27. So what that means is, if we say K1, we give K1 going to be your K rate constant. So K2, so the second rate had increased by a factor of 4.27. So K2 we can be considered as 4.27 K. Okay, and with that we can go ahead and do the calculation. Ln, so ln K2. So K2 now going to be 4.27 ln 4.27 K over K, because we use the factor that they give, the relationship, equals negative EA over R, and then converting temperatures to Kelvin, T1, T2 would be 452, and then T1 would be 437.5. So So K to K get cancelled. So you find what is ln 4.27 and then you solve for this part 1.452 minus 1 over 437.5. That would give you a negative value. So that negative and the negative right here will get cancelled. R is going to be 8.314. So you should be able to find the answer. Okay. And again you will get a big number 1, 2, 3, 4, 5, 6 digit number. And then you would divide it by 1000 to convert it into Kelvin, not the Kelvin, sorry, kilojoules. Okay, yeah, number 18. That's how you do number 18. And for number 19, a rate constant obeys the Arrhenius equation, the factor A being given, activation energy given. What is the value of the rate constant? So, what is the Arrhenius equation? Slides, and then the Arrhenius equation is this one right here. K equals A is the Arrhenius factor, exponent negative EA over RT. So you would be using this equation. Okay. K equals AE negative okay, EA over RT. R is again the gas constant and T is the temperature. What is the rate constant? So we want to find out the K. A is given to us as this value, which is 2.2 into 10 to the power 13 per second, and exponent activation energy is given to us 150 kilojoules. 150 kilojoules. Okay, and R is going to be, I'm going to write down it here, I need space, 2.2 into 10 to the power 13 per second, and E 150. Now this is in kilojoules, but the R value is going to be in joules. So because of that, I need to convert this 150 kilojoules to joules by multiplying 10 to the power 3 joules. Okay. Over gas constant 8.314 joules moles per Kelvin times the temperature 227. So 227 need to convert to Kelvin by adding 273. That will make it 500 is the temperature in Kelvin times 500 Kelvin. So Kelvin cancelled, and then this joules and this joules will cancel. So you would do the calculation in this part. Negative 150 into 10 to the 3. You divide it by 8.314 and 500 number. Okay. So if you do that calculation, see if you get a number like this. E raised to the power negative 36 is what I got. Check to see what number you guys are going to get. Okay, per second. And then you find out the anti-log of negative 36, and then you multiply it by 2.2 into 10 to the 13. So your rate constant will be in the units per second. Okay, that's how you're going to get the answer for 19. 20. The decomposition of dinitrogen pentoxide, activation energy given 102 kilojoules per mole, and the delta H for the reaction given 55. What is the activation energy for the reverse reaction? Now it says delta H 55, positive 55. When the delta H is positive, from the sign we can identify whether it is an exothermic reaction or endothermic reaction. Normally, exothermic reaction, delta H is negative. Endothermic reaction, delta H is positive. Let's say this is your reactants. Okay, always, so this is the reaction coordinate diagram. It goes to a higher value where it is activation energy, and it comes down. So if it is a positive enthalpy, it's going to be endothermic reaction. The product's energy going to be higher than the reactant energy. So the activation energy is given to us as 102 kilojoules per moles. That is the activation energy for the forward reaction. And enthalpy is basically the difference between the reactants and the products, and that is given as 55. It's asking what is activation energy for the reverse reaction. So the reverse reaction is if the product goes to reactants. So for the reverse reaction, activation energy is going to be the part that I draw with the red. So how do you find how much is that? So from here to here, 102, and then enthalpy is 55. So 102 minus 55 will give you the activation energy for the reverse reaction. Okay, so that would be the answer. Number 21. The kinetics of the decomposition of dinitrogen pentoxide studied at 50 degrees Celsius and 75 degrees. Which of the following statements concerning the studies is correct? The rate at 75 degrees will be less than the rate at 50 because the molecules at higher speed do not interact as well as those at lower speeds. So that's not correct. It says at 75 degrees, molecules at higher speed do not interact well. So that's not correct. The rate at 75 degrees will be greater than the rate 50 because activation energy will be lower at 75 degrees than at 50 degrees Celsius. That's also not true. The temperature doesn't decrease the activation energy. Instead, it would make the molecules more energized, so it will have more collisions, and as a result the reaction will speed up, right? So that's not correct either. The rate at 75 degrees will be greater than 50 because the activation energy will be higher at 75 degrees. That's not true either. Rate at 75 will be greater than 50 because the number of molecules with enough energy to react increases with increasing temperature. That's correct. Rate at 75 will be greater than 50 because the concentration of gas molecules. So that's not going to be correct either. Okay. Increase in temperature increases the reaction rate. So what is the reason for that? Increase in temperature increases the reaction rate. Activation energy of the reaction will decrease. Nothing will happen to the activation energy. More collisions will have enough energy to exceed the activation energy. Now that sounds correct. So B, greater fraction of collisions have the correct orientation of molecules. Temperature acts as a catalyst, activation energy of the reaction will increase. So the correct answer is more collisions will have enough energy to exceed the activation energy. Number 23, in an exothermic reaction, activation energy will change as the reaction progresses. That's not right. The collision energy of the reactants will be greater than that of the products. That's not correct either. The forward reaction will have a lower activation energy than the reverse reaction. That is true because exothermic reaction, meaning that the energy of the products is going to be lower. So this is the activation energy for the forward reaction. This is the activation energy for the reverse reaction. So the forward reaction will have a lower activation energy than the reverse reaction is the correct answer. The forward reaction is lower, the reaction rate will speed up with the time. Yeah. So C is the correct answer for that. 24. Consider the following mechanism for the oxidation of bromide ions by hydrogen peroxide in aqueous acid solution. We are given three reactions, three elementary steps. What is the overall reaction sequence for this process? So how do you find the overall reaction? Basically, you add these three together. So when you add up, we have H plus here. H plus here will make it 2H plus. And then we have H2O2. There is no more H2O2, so you add one H2O2 from the reactant side. And then we have H2O plus OH minus, and on the right side also we have H2O plus OH minus, so that can get cancelled. Okay, and then we have a Br minus, 2Br minus. Do we have Br minus in the other side? No. So 2Br minus bromide ions, and on the left side we are still having HOBr. We have HOBr, and on the right side also we have HOBr. That also get cancelled. Okay, and then from the right side, what do we have? We have a water molecule here and another water, so we have two water molecules, plus we have bromine that did not get cancelled, Br2. So you find the one that has this combination, 2H plus, 1H2O2, 2Br minus, two water molecules, and bromine. That would be the overall reaction equation. Consider the following mechanism. Which of the following rate laws is consistent with the mechanism? Now you see here, what do we have? We have a rapid equilibrium, slow equilibrium, and a faster one. Always we talk about that a reaction will have the rate as the slowest rate of the elementary steps if it involves more than one elementary steps, right? So this is the slow mechanism. So the rate determining step would resemble the rate of the slower reaction. So in the slower reaction, we have H2O plus OH minus and Br minus as your reactants. So then the rate has to be K, and the reactants are going to be H2O plus Br, no, H2O plus OH minus. That's what and Br minus. Yeah. So this should be the rate. K, H2O plus OH and Br minus. So pick the one that has this formula for the rate. Okay. Number 26. What is the molecularity of the following elementary reaction? Remember, we talk about in the lecture molecularity of an elementary step basically would be the stoichiometry or the molar ratio of the reactant components. So here we have one, here we have one. So it's going to be then bimolecular. Okay. 27. Which of the following affects the activation energy of a reaction? Number 27. Is it going to be the reaction progress that affect the activation energy? Can the presence of a catalyst affect the activation energy? Or the concentration of reactants, surface area of the reactants, or temperature of the reactants? So what's going to be the correct answer? Which of the following affects the activation energy of a reaction? So it's going to be the presence of a catalyst. Okay. 38. A catalyst accelerates a reaction because what does a catalyst does? Increase the temperature? No. Increase the number of molecules with the energy equal to or greater than the activation energy? Is that the correct answer? What catalysts do? No. It lowers activation energy for the reaction, supplies energy to reactant molecules, increase the number of collisions between molecules. So the correct answer is, we showed it with a diagram, that it lowers the activation energy for the reaction. When a catalyst is added to a reaction mixture, it slows down the rate of the back reaction, provides a new pathway for the reaction, increase the rate of collisions between reactant molecules, provides the reactant molecules with more energy. None of these choices are correct. So which one is the correct answer? It provides a new pathway or a mechanism for the reaction. We talk about this in the lecture videos also, so refer to that. Reaction intermediates differ from activated complex. Why reaction intermediates differ from activated complex? Activated complex is a transition state that normally you would find in the top place in an activation energy, potential energy diagram. So they are intermediate structures which have characteristics of both reactants and products. They are unstable and can never be isolated. All reactions involve reaction intermediates, but not all have activated complexes. They are molecules with normal bonds rather than partial bonds and can occasionally be isolated. They are stable molecules with normal bonds and are frequently isolated. So the correct answer is, reaction intermediates we can isolate, but the activated complexes we cannot isolate. In activated complexes we have partial bonds. In reaction intermediate we have complete bonds, full bonds. Okay, so the correct answer would be, they are molecules with normal bonds rather than partial bonds and can occasionally be isolated. So the correct answer for 30 is D. Okay. Alright then, so you should be able to complete your homework for chapter 16, which is kinetics. It's a great information and a lecture for you to learn about the reaction kinetics. I'll talk to you soon.